Good afternoon. My name is Chih-Ling. I'm from Rail Mechanics Group, University of Queensland, Australia. Today, I want to share with you is our study of wear debris in the grease-lubricated hexo bearings using an electron microscopy technique. So I guess my talk will be a bit different from the rest of it in the conference. How do I? All right. So in my group, we are very interested in look at the hexo bearing because it's a critical component for the rail vehicle in terms of the transportation safety. So we know that lubricating a bearing with selected and designed grease will decrease the friction and wear, which will increase long service life of the bearing. If a bearing has insufficient and inadequate lubrications, the wear and the friction will increase and that result in the generation of the particle in the bearing itself. So we know that the wear process and the debris accumulation inside the bearing is one of the most commonly bearing failure mode. So for the rail operators, doing periodic maintenance and replace the worn and damaged bearing are very costly. So in order to give an early warning of the bearing failure, the wear debris analysis has been introduced and used since the 1980s. So this technique has been used in the various machines and devices such as gearbox, turbine engine, electron motors. What we found is they look at the bearings used in this device, they detect the wear particle from the lubricant, or look at the wear particle, they examine to the damaged surface, and then they collect the particles, they examine them. But you also can do it in the experimental testing environment where you put the particle with known size and chemical composition, and then by using that way, we can study a specific the generation of the wear debris. So thanks for those studies, there is an established relationship between the wear particle they found and what type of the wear mechanism they found and the wear mode. So in this study, we're using this established relationship to be a guideline to look at the wear debris collected from the grease lubricated hexo bearings. Oh, watch your 7. Sorry. So what we found with the previous study is 90% of the study, they use wear debris analysis to look at the bearing system used in lubricating by the oil. So we know that 90% of bearing has been lubricated by the grease, and there's a difference between the grease and oil lubrication. So in the grease lubrication, we have additional additive and metal thickener. So it's very reasonable to assume that the generation of the wear debris found in the grease lubricant bearing is more complicated than that used in the oil system. That leads to the target of our study. We want to know whether the source of the debris we found in the bearing is internal or external. The second one is we want to know the material and the morphology make up these bearings. So these are the two examples where the grease sample in the field hexo bearings. In this project, we are able to examine 20 field used spherical bearings. They are very intense of their travel distance. So in the early life bearing, we have bearing travel around less than 0.05 million Ks, where in the medium use bearings, they travel between 0.3 to 0.6 million K. And we come down to the heavier use bearing, they travel about 2 million Ks. And the figure shown in the right-hand side is the sampling location where it's between the bearings and between the space between the cage and the rollers. So about 1,500 debris are analyzed through this 20 used bearing. This just give you a very simple diagram what the scanning electron microscopy is if you don't know. So we prepare the sample, we collect the bearing, collected wear particles, we coat it and then put into the vacuum chamber. Then we will have a focus beam, electron beam scanning on the sample. So you will have secondary electron image, which will give you the morphology and the topography of the samples. And there's an EDS detector sitting in the side, will capture the X-rays, and that will tell us the composition. So in the middle, that's the example how it looks like. We will see the composition of this particular debris is made of the iron, a little bit of cornelian and silicon. And in terms of the morphology of the bearing, we can see the pits, indents, and the scratch in the fracture surface. So we get in all this information and use the assembly relationship, we will identify this particle is a chunk wear debris. So in total, we find 7 types of wear debris in the field used bearings. Here is a graph plus particle type versus a total exam debris. So we found out the cutting wear and severe wear are very easy to distinguish because of the shape. Then we will have lamella particle, which normally turns out with a very thin shape like. And chunk debris normally have an irregular shape and they have a different surface deformation happening there. And then microspalling is very relatively small. There's about 1 micrometer thickness. You can find out when also attached with the severe particles. Then we have a severe sliding debris where they have a lot of scratch marks running parallel on the surface. Then the final one is a fiber debris, which is normally doing the self-tangle. When we talk about the possible origin of the wear debris, we found out both internal and external wear. So we found out most of the wear debris we collect from the used bearing are generated in the internal, which is they have a composition similar like a bearing particles or the cage coating material. The external wear debris generally are found in the operation environments because they contain silicon sand, airborne mineral dust, and carbon-rich fiber. So in this case, we found that the external debris only found in the heavily used bearing, and we think this is because we found out there's a lot of seal degradation happening. So we found a fragment of the seal in the heavily used bearing. So that gives us indication that external debris has a chance to come into the contact area. Now, because there's 7 types of wear particles we found, but there's very interesting 2 types of them we found within the different type of the bearings. So the severe particle we found, they have a different morphology, depends on the bearing usage. So this is the typical severe particle we found in the early life bearing, where they have the dendritic pattern, or they have a grain size pattern, or they have this melting sort of stage. Also, we found that there's a microspalling particles attached with the dendritic, with the severe particle with a dendritic pattern. Some of the particles have a hollow internal structures. So within this type of particle, we think it's generated during the very rapidly cooling stage on the melting, high temperature area. So you will see the particle form the dendritic pattern, and also because the particle is within the contact area, so it has formed the very perfect, almost perfect sphere shape. When we look at the severe particle collected from the medium use and heavily used bearings, you can see you almost cannot see the dendritic pattern or the grain size pattern. So they have relatively smooth surface. The other sphere particle we found has a smooth surface is the external wear, which is mostly quartz or silicon-rich debris. The only way to distinguish them is to do chemical analysis in order to find out. And you see with the silicon-rich particle, they have there's no dendritic pattern there, and there's no grain size pattern you can see. The other thing I want to share with you is the formation of chunk debris. Interested to see in the earlier life bearing, we think that the formation of the chunk debris actually from the broken of the sphere particle, which has dendritic pattern, if you can see that here clearly. So here we have roughly see the blue mark area as the original grain size, and we have in the fracture area we see the cavities and dendritic pattern there, and the one on the left hand side or right hand side show you the very clear image. So once this type of particle has been overrolling in the contact area, the size reduced, but you also see a lot of surface deformation, such as there's scratch marks. There's also a micro crack happening in the fracture area. And the particle showing in your right-hand side is actually the fracture from the cage coating material, which have a very smooth area, very smooth surface roughness, but because it has been involving in a different wear process, so you also can see the crack and the sliding marks. So just want to discuss a few discussion here. So we found that the formation of wear debris predominantly associated with the rolling contact mechanics because we found a high concentration of the chunk, lamella, and sphere debris. We also see the evolution of the iron-rich sphere particles. The formation is from the dendritic morphology with or without hollow internal structure to a very smooth surface. They are likely to be formed by a grinding process and rapidly cooling from the local melting stage. So the formation of a chunk debris in the early life bearing is likely to be formed due to the fracture in the sphere particle which has a dendritic pattern. The last one is a metallical wear debris generated naturally in the field-used bearing has more complicated surface morphology compared with those we examined from the external debris. Just go back to the very beginning, we want to address these two questions. So we found out 95% of the exam debris are generated due to the internal wear process. Only 2 to 5% of the exam wear debris are external sources. And then in terms of the debris, more than 90% of them are iron-based. 2 to 7% are highly concentrated of the cage coating material. 2 to 6% are from the external sources. So the variation of the surface morphology on the sphere and the chunk lamella debris, they vary. It very depends on the traveling time of the bearings. So the final one is we want to thank our funding party, which is Real Manufacturing CRC back in Australia, and the support of the University of Queensland. This project is part of the hexo bearing maintenance optimizations. So the data we're presenting here were used into one of the PhD's modeling to predict the lifetime of the field bearings. Thank you.
Many thanks, Chih-Ling.